So in the previous lecture, we took up an example on adsorption in single stage and two stage counter current stages. Okay, two stage counter current. Okay, and there we had an example of charcoal or carbon used to remove oil, remove color from wastewater. Okay, and there we showed that the amount of adsorbents required in two stages is smaller than that required for a single stage. So whenever, and that time also we said that if the number of stages are fixed, then to calculate or to determine the amount of charcoals or solids required for adsorptions, one has to do some iterations. So even if you do graphically or you solve analytically, then there is some iteration required for this. Today in the example, we take the same example, same system, charcoal and color, this color in wastewater, and we take up this example on two stage cross current. Okay, so instead of counter current, now we have two stage cross current. So you have a feed brought in contact with charcoal, treat that feed, allow for the equilibrium to reach, take out the feed, bring to the second stage. There again you treat with the fresh charcoal, and they determine how much amount you have total required for this cross current two stage process. Okay, here also we will see that in some cases we can require, we need to do these iterations to determine how much amount of charcoal is required. So let's take this example on two stage cross current for charcoal and wastewater system. So we have this two stage cross current adsorption, and we have this carbon or charcoal plus this wastewater. Okay, so what you will have is one stage here and the second stage. You have this feed, say flow rate is Ls, and Y0 is the amount of, or the weight fraction of color in this is stream wastewater. So generally, for this Y0 we said that we can have kg or certain units of color per kg of solutions. So let's say that Y0 is given as 9.6. all right, and Ls, let's say we have 1000 kg of water to treat. Okay, so again here we can have 1000 kg or we can have 1000 kg per second. So both are acceptable. All we are trying to say that if we work on batch, so we have to do it twice. So here the basis, if we choose 1 second, then also we have this 1000 kg of water. So now we bring in contact with solid. So we have GS charcoal. Let's say it's a fresh charcoal, so 0 concentrations, and here also we can have kg per second. If you have kg per second, if we talk in terms of kg, how much kg we are, kg of wastewater, then here also we can have just kg alone of solid charcoal. So after treatment, this concentration is now Y1, so kg color of units per kg, and here also this is kg of color or certain units per kg of carbon. So after treatment we have this X1, this is GS, GS will remain same as this, similarly LS will remain same as this, and here we have this Y2. So we are working solid free basis, and now we bring in contact with again some different GS, maybe you could put GS2, we have GS1 here, this is also fresh carbon, and after this we have this X2, this is GS1, and we have this GS2. Amount of solvent is Ls. All right, the question asked here is that what is the max optimum amount of solvent required, or sorry, charcoal required. So we have to optimize this minimum amount of charcoal required. So this flow rate of GS1 and GS2, they are not known. We are assuming ideal stages, so X1, Y1 determined by the equilibrium, X2, Y2 determined by this equilibrium. So let's see again, we have 1000 kg per second of flow rate, say solutions, wastewater containing 9.6 units. We have been asked to reduce this unit to Y2 as 0.96. So 1/10 time reductions. So this problem is the same as in the previous class, except now we are working on two stage cross current. Okay, and the question asked is that what is the amount of GS1 and GS2, so that total amount is minimum here. So one can solve again analytically and graphically. Let's write down the equations which we have here. LS Y0 minus Y1, so that's a reduction in the color amount in wastewater. This will be same as GS1, and whatever it picks up, X1 minus X0, but X0 is 0 here, so we have GS1 into X1. And Y1 and X1, they are determined by, they are in equilibrium, so they are determined by this some isotherms. So we can write Y1 as equal to m x to the power n, alright, or mx1 here. Similarly, we can write for the second stage ls y1 minus y2. So reduction across the second stage, this should be equal to gs2, x2 minus x0, x0 is 0 here, and then y2 and x2, they are on the equilibrium, so y2 equal to m x2 to the power n. So gs1 is not known here, gs2 is not known here. Y1 is, of course, you must notice that it's an intermediate here, it's an intermediate variable. So the question asked here is that what is the maximum, what is the minimum amount of solid required. So essentially we are going to optimize this. We did it earlier, the previous lecture. dy1 equal to, we will set this to 0. So y1, because y1 is the intermediate variable here. Again, go back to the stage configuration we have. Stage 1, stage 2, this is y1, this is y0. This is gs1, x0 is 0, we have x1. This is again x0, but now we have gs2, this is x2, and now we have this y2. So if we vary the amount of gs1, y0 is fixed, ls is fixed, x0 is fixed, and we say that the two exit streams are in equilibrium, or it means that y1 or x1, this is a function of gs1. So once we change this gs1, y1 will change, x1 will also change, they are in equilibrium here. But once we fix y1, y2 is fixed to us, and these two are in equilibrium, so we know x2, that means the amount of gs2 is also fixed. So essentially one has to optimize the total amount gs1 and gs2. Should we take a very large amount in the beginning, or should we take a small amount in the beginning? Okay, and we did this exercise. You write down the two equations, eliminate ls and gs, and we have only one variable left here, which is y1 as an intermediate. If you differentiate, equate to 0, we have the conditions given as y1 over y2 to the power raised to the power 1 over n minus 1 over n, y0 over y1 equals 1 minus 1 over n. So this is the equation we obtained in the previous class. So we have this expression for this. Now let's get back to our example. So if you recall, we have the equilibrium curve. We did some calculations here, so we won't repeat that. We will start from the same example of color in wastewater and color in charcoals. So if you recall, we had certain unit of color per kg of adsorbent, which is charcoal here, and here we had some unit of color per kg of solutions. Again, when you use these solutions, actually we should have been working on a small y as per the conventions, and we should have used x small x, but we said that it's a very dilute solutions. Capital X is approximately same as small x, and capital Y is same as a small y. So we did this exercise in the previous class. We have now the numbers here: 1800, 825, 663, 395, 223, and corresponding to this we have say 9.6. So that's your starting material, 9.6. Then we have 8.6. These are all equilibrium values: 6.3, 4.3, 1.7, and you have 0.7. So this data, these data are given to us. Okay, all we do, we substitute in these equations. So let's rewrite down these equations. Y1 over Y2 raised to the power 1 over n minus 1 over n, Y0 over Y1 equals 1 over n. And if you recall, we had the slopes of ym, y equal to mx to the power n. N was given as, or n was obtained when we fitted this equilibrium curve on log scale. We obtained values of n as 1.66. Okay, so now we can go back, and m was, we can write down 8.91 into 10 power minus 5. So now we can put back here y1 is intermediate values. We're supposed to know what we're supposed to calculate from here. Y1, Y2 is the exit concentration of treated wastewater, which is 0.96. So we're going to reduce from 9.6 to 0.96. Minus 1 over n, which is 1.66. Here we have 1 over 1.66. Y0 is 9.6. And Y1 we are going to calculate equals 1 minus 1 over 1.66. So you can see that Y1 has to be solved by some trial and error or by iteration. It's a non-linear equations. Of course, this number is check 0.397. So if you solve by some iterations, maybe left hand side equals right hand side, you know, one of the very old techniques to calculate this Y1, you should get Y1 as 3.3 kg or some unit of color per kg of solution wastewater. Okay, so in fact, if you want to put the values of Y1 here, 3.3 over 0.96, then we have raised 1 to the power 1.16. You will see that left hand side and right hand side are very close to 0.397. Okay, so you have to improve, you know, how much accuracy you want to solve this techniques, or maybe some numerical technique can make use of it. If you have, you know, taken some course on numerical methods, you can solve for this Y1. So once we have this Y1, now we can go back and calculate X1. So again, let's draw very quickly the schematics. We have 1, 2, this is X1 here, and this is Y1. This is Y2, this is X2, this is X0, X0, both are 0, and here we have this Y0. So Y0 to Y1 and Y1 to Y2. Y1 X1 are in equilibrium, Y2 X2 are in equilibrium. LS is known to us. We want to find out GS1 and GS2. So to calculate GS1, we have to make a balance around this. We have to determine this X1, but X1 is in equilibrium with Y1, or the two streams are in equilibrium, so we can write X1 as Y1 to the power m raised to the power 1 over n. So Y1 over m raised to the power 1 over n. Y1 we have calculated 3.3 by iterations or by some numerical algorithms. M is the slope of isotherms, friendly isotherms, which we fitted in our previous example through the equilibrium curve, 1 over 1.66. This you should be able to obtain as 565. So 565 units of color or kg of color per kg of carbon adsorbent. So this is the X1 solid phase concentrations in this living stream. It's a solid phase concentration. 565, which is in equilibrium with 3.3. In fact, if you go back to this graph which you have obtained with the slope of m, if you read Y1 as 3.3, some values here, you should be able to obtain, you should be able to read this number 565 directly from the graph. In other words, if you have this yx on log scale, right? So we have y equal to m x to the power 1 over n log y equal to log m plus 1 over n log x, and from this we obtain the values of m and n. So we have this friendly isotherms linear on log plot. Y1 read, Y1 we have just now calculated 3.3. Read from the graph, this should be equal to 565, or you can solve from the equations. Once we know the values of y1 here as 3.3 and 565 as x1, you can make a balance which we did earlier. For the stage 1, S1 will be equal to LS, which is 1000. It contains 9.6. We have brought this minus to first stage to 3.3. So 1000 9.6 minus 3.3, and the solid phase concentration has increased from 565 to from 0 to 565. So S1 is 11.14 kg. Mind you, once we have S1, now we can determine S2. S2 is by the same method. We make a balance around the second stage, 1000. This remains the same. Now we are going to reduce from 3.3 to 0.96. So that's why we said this y1 is an intermediate variables. Divide by, now we have, now look at this, we should have 270 minus 0. So what is this 270? Go back to this schematics, stage 1 and stage 2, x0, x0, we have y0, x1 and y1 in equilibrium. So similarly we have y2 and x2 in equilibrium. So if we know y2, which we know here 0.96, we should say that we can go back to this curve. Let's see here, this is 0.96. Read from the graph, we should be able to read this number as 270. So we have this number 270 and we have number this 565. Or alternatively, again you go back to this number, x1 equals, or x2 equal to y2 over m to the power 1 over n. y2 is 0.96. Slope of the curve we have obtained is 8.91 10 to the power minus 5 raised to the power 1 over 6, 1.66. This number will also be equal to 270, or kg of color per kg of adsorbent. Alright, so now we have S1 and we have calculated S2. This number, if you put it here, you should get 8.67 kg. So the S min, why min? Because we have differentiated to obtain y1, right? So we obtained this min, we had, so this is actually GS1, our previous nomenclature, dgs over dy1 equal to 0. So this is what we set it here. So we have S min. If S min is, so if you calculate, add the two, 11.14 and 8.67, we have 19.81 kg of carbon or color, sorry, kg of carbon per 1000 kg of wastewater. So that's the answer, 19.81 required for 1000 kg of wastewater. Let's see how we can solve this graphically. Okay, so if you want to solve graphically, or at least you should be able to represent on the graph. So we start here with y versus x, maybe on the linear scale, because operating line is linear on this linear scale. So we have the same equilibrium curve. Now we have y equal to m x to the power n. Okay, let's mark the points here. So we know y0. So again, let's focus on these two stages. We have y0, y1, y2, we have x0, x0, we have x1, we have x2. Two are in equilibrium, two are in equilibrium. y0 is known to us, y2 is known to us, x0 is known to us, x1, x2, x2 we can find out from this equilibrium is known to us, x1 is not known to us, nor y1, nor we have this value of gs1 and gs2. Okay, so stage 1, y0 and x0, two incoming streams. So x0 is 0 here. We know this, we can locate this coordinate here. Okay, and at the end we have this y2, which is 0.96, and corresponding to this y2 we had this calculated x2 which was 270. Alright, so we can mark this point here. This is x2 and this is y2. y2 equals 0.96 and y0 equal to 9.6. x2 is 270 if we read from here. Alright, now how do we get GS1, GS2 and y1? We do not know the slope. For cross current it's a negative slope of GS1 over LS, so all it means it requires iterations. So let's take an arbitrary curve like this. That means we have assumed certain slope or we have assumed certain amount of solid. So essentially we have GS1 LS minus of this negative slope here, and when we reach this, so that's your y0, this is brought down to y1. Alright, so this would be your values of your y1 here, corresponding to which you will get x1. But why iterations? Because now if we know y1, which we know here, say with this first guess, then if you connect this y1, now y1 is brought in contact with x0 again, now we get the final concentrations of y2. This line will be now fixed. Alright, so try to understand what we are saying here, that we do not know the amount of GS1. So we assume a value of GS1, we reach this y1, so this stream starting from y0 is brought down to y1. So y0, x0 enter and they leave at x1, y1 in equilibrium. Now y1, x0 equal to 0, again they enter second stage and leave as y2 and x2. This point is already fixed because this is 0.96, so and this is 270. This line is fixed. Once we know y1, we can connect with this. So now we have from the slope, now we know GS2 over LS. So we calculate GS1 plus GS2. Guess 1. Right? So calculate this, get the amount here, total amount GS. Take another slope here. Suppose I choose this slope. Alright, that means it's a new values of y1, or it's a new values of y1 here. But once y1 is here, now we have new values of GS2 over LS2. This will give you different values. GS1, GS2 has different values. Choose another guess here. This is y1 again. This y1 is in equilibrium with x1. This is also with x1, new values of x1. So we know now new y1. Once this y1 is known, we connect with this, we have now different values of GS2. So one has to make this guess here and see which way it falls, which number gives you the best or minimum amount of GS min. And if you do this exercise graphically as well, so you have to take several of this, you must be able to convince yourself that you are getting the same numbers. Maybe this is x1, which should be equal to 565. And alright, so this is your x1, and what y1 you will get here, this was 0.96, corresponding to this 565, this number will be 3.3, same as before. So let's redraw this curve again, assuming that we have reached right guess, right values, which gives you minimum amount of solvent or charcoals, solid. So we have this equilibrium curve. We start with y0, x0. We have this number, so this stream gets, so a stream concentration of wastewater decreases till we have this equilibrium concentration, exit concentrations, which is x1. x1 is 565, corresponding to which we have now 3.3. So this y0 was 9.6. We have brought down from 9.6 to 3.3. We have to get down to 0.96. So this number is fixed here, 0.96, and corresponding to this value is fixed to 270. All right. So all you do, if you connect this, get this GS1. This from the slope of GS1 over LS. If you calculate, you should get GS as 11.14 kg, and from this slope GS2 over LS, if you calculate GS2, you should be able to get 8.67 kg. Or look at from this, the slope of this curve is tan theta, this divided by this number. Okay, so GS1 over LS is nothing but this by this. From this also we can get GS1. And similarly for this, here we have 3.3, this is 0.96, so this segment divided by this segment 2.72. From this also we can get GS2 LS to obtain the same answer as before. Alright, so what we have obtained here is, we have the same message. Whether we solve analytically or we solve graphically, there is an iteration required, and this always happens when the number of stages are fixed. So if you are told that we have been given 2 stages, 3 stages, 4 stages, then calculate the amount of charcoal required or amount of solid required for the treatment of the feed, then one requires iterations, whether it's a cross current or it's a counter current. However, if solvent or the amount of solid is given, solid phase concentrations, then how many stages are required, that should be straightforward. For example, you can go back to this. If you are told that this amount of GS1 is given, the amount of solid is also given for the second stage, how many stages are required? Well, we start from here. This was stage 1, then you have stage 2. So if the solvent is given, the amount of solid is given to us, solution is given to us, then the slope we can find out. There's no iteration required. We can we can come to this equilibrium curve and calculate this intermediate numbers. Then we know the second slope, GS2 over LS. We can get this number here, which is y2 equal to 0.96. So whenever we have this question of phrasing the problem, one has to understand and one has to be careful, both mathematically, analytically. There will be iterations if stages are given and the amount of solid is asked to determine here. Okay, so these are the 3 examples we have chosen on adsorptions stage wise, and here we are saying that 2 living streams, solid and liquid, they are in equilibrium. What we do now next is batch adsorptions. So when we say that we have calculated this isotherm, you must have recalled that we did very small like experiment. We had took a beaker, take some wastewater or whatever solutions you have, add adsorbents. So we have adsorbents, adsorbate, and a small batch beaker. Allow for the equilibrium to reach maybe 10 hours, 24 hours. Then calculate the concentration in this solution phase. Take the difference. The difference will tell you how much amount has gone on the solid. So given the final concentrations, what is the amount in the solid, that will give you the equilibrium curve. What we want to know, how long will it take? Alright, so there are certain processes which are also batch, especially the wastewater treatment, or in pharmaceutical industries you have certain small amount of feed which you want to clean, purify by adding certain solids. Okay, in that case it's a batch adsorption, and one would be interested to know how long will it take to bring down one concentration level from one to another. Maybe the final concentration is in equilibrium. So that type of a small exercise we should be able to do in today's lecture. One thing again, if you recall, we talked about this adsorbents, different type of adsorbents. One is porous, one is non-porous. Of course, not many people will like to work on non-porous because it has a small BET area, small surface area. So it has a small number of sites. Everybody would prefer in general to have large amount of BET area so that you have very good number of sites, and for a small amount of adsorbents you can remove very large amount of adsorbent. Okay, so again from the mass transfer point of view, or whatever you have learned in this course, if you take a solid adsorbent, bring in contact with this some solutions feed, then what are the rates involved? Well, if there is a flow or you can have a stirring, so there is a Reynolds number. Given the Reynolds number, there will be a film mass transfer coefficients. So that's one rate. At what rate the solute or the color is transferred from the feed to the solid surface. So that's one rate. Once it gets onto the solid surface, then it has to diffuse inside the pores, because this is your porous adsorbent. Charcoals, very large BET areas, 2000 meter square per gram or 3000 meters square per gram. So then the solute has to diffuse inside the pores. So that the second rate of diffusion, Knudsen diffusion, pore diffusion, we have talked about those earlier. And then once it diffuses inside, then it has to adsorb and desorb on the solid surface inside the pores. So you have the third rate, which is rate of adsorption and rate of desorption. So whenever you have 3 rates in series, again you should inspect it and see which rate controls. This also we have discussed, when we talked about the two film resistance. Whenever you have two resistances in series, then one which is smaller, very smaller, controls the entire mass transfer rate. So here you have three rates. One rate is rate for mass transfer from the bulk to the solid. We call it interface mass transfer. Then you have the pore diffusion, inside color diffuses. So you have intraphase mass transfer. And then once it reaches on the wall, then it desorbs. You have third rate, a rate of adsorption, rate of desorption, first order, second order, given by Langmuir kinetics or Freundlich kinetics, some arbitrary kinetics, etc. So in that cases, now what happens? One, it's a good practice to make an estimate that which one is controlling, right? If all three of them, they have the same order of magnitudes, then all of them have to be taken into account in the solutions, right? But if one of them is much smaller than the other two, then you can say that the process or overall adsorption is controlled by that rate, and the rest of the two steps are in equilibrium. So in case of porous solid, it's very common that it's always, most of the rates are determined by the pore diffusions, or at least by the rate of adsorption desorptions. Bulk phase from the solutions to the solid surface, generally you have very large Reynolds number, whether you have a stirring or you have some tubular coated, some tubes you have coated with the solid adsorbents, or you have packed bed. Generally you have a very large flow rates. So interface mass transfer is never controlled. It's always very large, or at least the user can choose a very high Reynolds number. So that situation never occurs. But then, as far as mathematics is concerned, if you recall from our previous lecture also, when we wrote down the equations, then the second stages, or when you have the pore diffusions, or when you have rate of adsorption desorptions, then mathematically it's very difficult to solve. You have a set of partial differential equations, set of ordinary differential equations. Okay, so unfortunately, in the real world, you have rates determined by pore diffusions or by adsorption desorptions. Very rarely it happens that it's an rate is controlled by the interface mass transfer. Okay, but we have to solve the set of PDEs by some programming or some different numerical algorithms. But in today's lecture, just for the sake of continuity, we assume that our pore diffusion is rate of adsorption desorption is controlled by interface mass transfer. So that means we will say that inside the solid surface you have a very fast kinetics, or diffusion rate is very large. So as soon as the solid comes inside, it diffuses inside. There is no concentration profile inside. Remember, whenever there is a resistance, there is a drop. So we are saying that all drops occur outside the solid surface, not inside. So inside there is no concentration gradient, there is only one concentration, we call it X. And when it adsorbs and desorbs, then also it's a very fast kinetics. So whatever we have concentrations in the liquid phase or gas phase outside the solid surface, we assume that the solid phase concentration is also in equilibrium given by this isotherm. So it's a very simplified case, but for this undergraduate level, we have to do this exercise. We assume that it's interface which is controlling. In the real world, of course, it's the other way around, but then solving that set of equations becomes very cumbersome. So let's get back to start this new topic for this adsorption, which is batch adsorption. Okay, so we start with this batch adsorption. So what we are talking here is stirred vessel. Okay, so we have a beaker, let's say certain wastewater, certain volume, C initial concentrations, maybe color, maybe some benzene, xylene, toluene, and we have the solids, charcoals here, or adsorbents. And what we do here is stirring. So there is a little bit of stirring here also, so that concentrations inside it's well mixed, but not to the extent that mass transfer coefficient in the interface is very large. So let's get back to this. We have volume, certain C initial concentrations, we have certain adsorbents here. Let's say particle size is dB, total weight is W, we know its external surface area, we can call it meter square per gram. This is known to us. Okay, of course this solid adsorbents, if you look at slightly magnify, maybe they are porous. right? But we are saying that this diffusion inside is very fast. In other words, if we draw schematically, we are saying that if this is your bulk phase concentration, say C milligram per liter of color in this liquid, then all drops occurs inside this film. So this is given by Km or KL, mass transfer coefficients, which is a function of Reynolds number and Smith number. We have done it before. This Reynolds number will be based on the RPM of this stirrer. Okay. So essentially all drops occur in this, and inside there is no drop here. So if you look at one pore, the reality is that this species get inside and then they adsorb and desorb at the wall at certain rates. But we are saying that this is a very fast kinetics. There is no gradient here. So at any time, if you look at this adsorbents and you have the solutions surrounded by the solutions, what you have here is, to start, say this concentration is Y0 here, and it's a fresh adsorbent, so there's no concentrations here. After some times this concentration will drop and this will increase solid, but look at this, there is only one concentration here, X. So there is no concentration drop here. Why? Because we are saying that interface mass transfer is controlling. Pore diffusion or intraphase is fast. Intraphase mass transfer is fast, or diffusion resistance is smaller here. Okay, so with the time this concentration will drop, color will change in the wastewater from Y0 to Y1 to Y2, all function of time, and this concentration will increase. But if increase, there's only one concentration level here, and at the solid surface, whatever concentrations we have here, say Y1, then we have corresponding this X1, but Y1 X1 they are given by this isotherm. So next time if it's Y2, this concentration has increased to X2, we have another isotherms here. Alright, so every time liquid phase is in equilibrium with the solid surface. So this exercise or assumptions have two consequences. One, there is only one solid phase concentration level. Okay, no concentration gradient inside. And number two, solid phase concentration, which is X, and liquid in our case, or maybe gas phase concentration Y, they are given by this equilibrium, Y equal to mx to the power n, say friendly isotherms. So these are the consequences of our assumptions that this is interphase mass transfer control. Alright, so with this assumptions and our understanding, now we can make some calculations. Just for one more, for your analogy, if you recall, you may have done in heat and mass transfer, or just heat transfer. When we take a solid, hot, say solid, temperature say T0, and immerse in cold water, TW, if thermal conductivity of this metal is very large, then you will experience the same thing. The temperature will be uniform here, and whatever drop occurs, that drop will occur across this film here. Similarly, a solid surface can also be heated in that case, and if it's say iron, copper, very high thermal conductivity, one temperature, all temperature gradients will be appearing only in this film transfer, which is a liquid transfer. So this is the same analogy we are making here for this solid adsorption also. So that's our physical understanding. Now we can set up, or we can make some calculations. Okay, so let's draw this schematic. Say we have a solid, say the radius is Rp, charcoal, particle density is, let's say it's rho p. It's immersed in wastewater So there is a film mass transfer coefficient KL. We have certain concentration level Y, which changes with time. So to begin with, this is fresh, Y and X, then it decreases, and this level will increase here. So right, so this is say Y1, we can write X1. When we have Y2, we have this X2. Okay, and inside there is no concentrations, so it's all one gradient here. So let's see how we can make this balance here. So we have, let's say V is the amount of solution, it's a batch, certain liter, let's say, and rho L is the density of the liquid. So kg per cubic meter. Let's say Y0 is the kg per kg. So this is adsorbent, or this is solution actually. And here you have this certain impurity. Let's say again it is color. So at what rate this color changes? So you have d by dt, V volume into rho L into this Y. So this is your kg per second. In 1 second, so much concentration of this water or wastewater, it changes, right? It decreases. So minus sign here. Why does it decrease? Because there is a mass transfer into this. How does mass transfer takes place? It's because of interface mass transfer. So there is a KL mass transfer coefficients. There is Y minus Y surface YS. So this YS is, let's say, at the surface at any time. So we have Y, it drops to this YS. Okay. Now let's, before we write some other terms, let's see that what we have here. This KL Y minus YX, you must recall this is a flux. So let's say we have chosen these values of Kx, so that the flux is kg meter square per second. Recall earlier we used to use moles per meter square per second. So here in case of adsorption, we are working on kg per second. So the flux is kg meter square per second multiplied by this AS. So what is AS? AS is the external surface meter square per kg. So this is a meter square flux. So we are talking of this flux across this. So meter square per kg multiplied by this W. How much amount of, what is the weight of this solid solvent? So this is a W kg. Okay. So see that is kg per second. How much kg per second of color is lost? Whatever is lost here, it's a gain or is transferred across the film to this solid surface. So we have the flux kg per meter square per second multiplied by meter square per kg multiplied by W to make it kg per second. So that's the solid balance. Okay. Now we can write as V rho L is constant. So we have minus d of Y over dt equals KL AS W. Let's put it together here, and we have Y minus YS. But what is YS? YS is surface phase concentration, or concentration of solutions near this solid surface or at this solid surface. And we said that because of our assumptions that everything is controlled by this interface mass transfer, and the kinetics are faster here, whether it's a diffusion kinetics or it's a pore diffusion kinetics, YS is in equilibrium with this X solid phase concentration. So we have, let's say, this X here. So Y equal to, we can write M X to the power N. Okay. So now we have Y, Y and X. So one equations, but both Y is a function of time and X solid phase concentration is also a function of time here. Okay. So one has to eliminate this. Now one can also make total balance at any instance. See, we starting with Y0. So at any time, if the concentration is Y, that means Y0 minus YT, so much kg per color, kg of color per amount of per kg of this solution has been transferred or has been moved to the solid phase. So Y0 minus YT multiplied by, say, rho L into V. So this is a total amount which has been transferred from 0 to this T time. And where it has gone? This has gone into solid. and solid phase was initially was x, right now it's x mole fractions kg per kg. Initially maybe it was 0, x minus 0 into w. So this is the second equation. Alright, so this is the rate, the rate expressions. In 1 second, at any time, what is the rate at which this wastewater concentration decreases? Why does it decrease? Because there is a transfer flux, and we are saying that the solid surface the two phases are in equilibrium, so y is equal to mx to the power n. But what is x? X is nothing but is starting from 0 at any time. This x is a solid phase concentration. How this concentration has increased from 0 to this? Well, over a time of t, 0 to t, we have the concentration has come down from y0 initial values to any time yt. You make this balance. Concentration of this has increased from 0 to x. You have x minus 0 into w. So 2, if we put together, now we can set up these equations. Dy by dt, already have rho l into v on the left hand side, kl, y minus, now you have y0, so we are replacing now x, y minus or ys was in terms of m into x, so now we have y0 minus yt rho l v over w. Okay, and you have here say mx, so you have m entire thing raised to the power 1 over n. Alright, so y minus m, okay, and here you have this everything x to the power n, so everything should put raised to the power 1 over to the power n, into we have this as and we had this w. Okay, so essentially now we have y. We can write down this expression as dy by dt equals some a b y minus c, and then one can integrate with dy over b y minus c equals dt. You can put this t here, starting with 0 time, how long will it take to reach this t time, sorry 0 and t here, and we have y0 and we have this yt here. So we can have this calculations, this integrations here to calculate how long will it take to reach this concentration, say y0 and yt equal to maybe y final, t equal to total time here. Okay, so this balance, this equations, so we can immediately apply. Let's take a very small example here. So this example, we have the same, say this wastewater, or let's say this is kg, certain kg of oil. So 1000 kg of oil, it has certain color, okay, say fraction is y here. We bring in contact with the solid, some charcoal, so this is x phase here. Let's see, we have the equilibrium y equal to 4.2 10 to the power minus 4 x, so essentially n equal to 1 for our simplicity. So kg of color per kg of solid phase, and here we have kg of color per kg of this oil phase. Let's say we have AP, surface area of this charcoal, as 25 meters square per kg. This AP is same as we have used nomenclature, maybe AS. Rho L, oil density is 950 kg per cubic meter. Let's say we have KL as 0.012 kg per meter square per second. Look at this unit of this. All it means, we have the flux given as this KL into y minus ys. Alright, so this is kg per kg, one in the bulk phase and one is in the solid phase. So we have KL kg per meter square per second, and we have this dimensionless quantity here. So KL is given 0.012. You have to be careful what unit is given for KL, so that we can write this flux. Okay, so this flux is kg per meter square per second, same as this unit of KL here. Amount of W adsorbent which is taken here is, let's say, 25 kg. Question is, how long will it take, say, to reduce the concentration level starting from y0 50 to YF1. So this is all 50 kg per kg or unit per kg, starting from Y0 to YF. Everything is given here. We can make a start from the fresh balance very quickly. D over dt, 1000 kg already we have, this into Y. This will equal to KL, Y minus YS. So this is a flux which is kg per meter square per second multiplied by AP, which is meter square per kg of solid into W kg here. So this is a total balance here. All you do, we just put the everything together here. You must obtain this as 625 into 0.012 Y minus YS, and YS we write as M into X. Alright, so what is this M? M is also given as 4.2 into 10 to the power minus 4 here. Okay, so all these values are given here. KL is 0.02 here. AP weight was 25 kg. AP we had 25, so 25 into 25 is 625 here. 0.02. We have 1000 here. All right, and this number is 0.02, 4.2 10 to the power minus 4 here. Okay, so with these calculations, now again we need to replace this X. So we have Y0 minus Y starting here into 1000 equal to X into W, 25 kg. So from starting from time equal to t equal to 0, concentration has come down to Y. So much into 1000 kg of oil we had. So much kg has been transferred to make the concentration of the solid phase rise from 0 to X in 25 kg. So all we do, we replace X in terms of all these known quantities here, dy by dt. This will be equal to, multiplied by this is 7.5. Y minus M, M is 4.2 10 to the power minus 4. X is now 50. So this is 50 minus Y. 25,000 by 25, we have now 40. All right, no raised to the power 1 over n here. So we have this, simplify further. This is 7.5, 1.0168 Y minus 0.84. We bring it down, dy over 1.0168 Y minus 0.84, and here you bring this dt this way, 7.5 integrate 0 to t, and here the concentration goes from 50 to 1 with the minus signs. Calculate t equal to approximately 12 minutes. So we got the answer that it takes 12 minutes for the solid phase concentrations to build up from 0 to this X, which we have replaced. Now we can go back, and once we know the values of this Y here, the last concentrations, we said that it has to drop to from 50 to 1. So corresponding to this 1, we can write down Y equal to mx again. X is 1 over m. So whatever we have here, solid phase concentration rises from 0 to corresponding to this X here, when the water concentration decreases from 50 to 1, and it takes 12 minutes. All right, notice that this is the first order here. So to reduce 50 to 0 or any value, very small values, it will take a very long time. It's all, if we can plot it here, it is the first order starting from Y0 to a very small quantity here. So this example we have chosen on batch adsorptions. So we of course qualified by saying that all resistances are negligible, and it's only interphase resistance which is predominant. So diffusion resistance in interphase mass transfer is significantly higher. Why it is higher? If you recall our previous lectures, Reynolds number is poor, maybe stirring rate is poorer, okay, flow rate is small. So all resistance occurs across the film around the solid surface. Inside there is no resistance, or resistance is negligible. Kinetics is very fast here. So we have only 1x concentrations, and this concentration increases, wastewater decreases, and all the time at the solid surface, liquid phase or the solution phase concentrations is in equilibrium, or solid phase is in equilibrium with this solution phase. So with that approximation, it seems we can solve it analytically. Otherwise, if you allow for rate inside, finite rate inside, by pore diffusion or by rate of adsorption desorption, then things become more complicated. So that maybe we're learning at a higher graduate levels, where you set up this ODEs or partial differential equations and then make use of certain numerical method to do this kind of predictions here. For us, for the third year levels, this kind of simple example for batch adsorption is good enough. Okay, so let's sum up today's lecture. So far we had 4 lectures on adsorptions. We started with the very basic of adsorbents, characterization of adsorbents. So we talked about the BET area, pore size distributions. Then we talked about thermodynamics, isotherms, Langmuir isotherms, Friendlich isotherms. Then we said the process could be 2. One is stage wise and one is a column wise. In stage wise, we talked of one stage, single stage, then multi cross flow stage, multi stage cross flow, and then we had this counter current flow stage. So these are the stage wise operations where you say that the 2 living streams are in equilibrium. We can also have the rate processes, and one very small example we took it in today's lecture, where we say that, well, we have the rate, but the rate is controlled by this interface. Okay. Now when we meet the next time, then we take up our study on the packed bed column. So our approach is similar to the previous example, previous unit operation on absorptions, where we have this continuous packed bed column, unlike extractions where we had stage wise. So adsorption can also take place in a batch where you have packed bed like this this example, or you can have a column where there is a continuously flow there, right? So we have a column packed with certain adsorbents, could be porous, could be non-porous, bring in contact with certain solution, solvent, or gas phase, liquid phase, which you want to treat, and then monitor the exit concentrations, right? So over a period of time, let's say the concentration will be very small, slowly it will pick up till this bed becomes saturated. All right, once it becomes saturated, one has to stop it and one has to regenerate it. So this is the end of today's lecture. We will see you the next time.